Hello, I'm Sang-Hyun Choi from Samsung Research, where I am currently heading Advanced Communications Research and Standardization. In this talk, I would like to share our view on technical challenges and prospects towards beyond 5G and 6G. Since the very first commercialization of 5G in April 2019, global-scale 5G commercialization has been occurring around the globe in a very fast pace. As of Q1 this year, in 68 countries, 162 operators are providing 5G service, with the total subscriber number stands at 389 million. Note that Asia-Pacific region is leading the commercialization with over 300 million subscribers, while America is catching up with over 50 million. Mobile cellular communications technology has been evolving since its first generation was introduced around mid-1980s. As you see at the right bottom, a new generation has been introduced roughly every 10 years. While 5G commercialization started just 2 years ago and its deployment is still actively ongoing, we already started 6G research with the commercialization target around 2030, since it takes years for the technology development and its standardization. Given that 5G is officially called IMT 2020, we expect that 6G will be called IMT 2030. 3GPP is a prominent organization with the industry participants from different countries, and it has been developing mobile communication standards since 3G, and now even up to 5G. In fact, 5G standard itself is not a single set of fixed technologies, but it has been evolving too. Most of the earlier 5G commercialization were based on Release 15, while the standardization of Release 17 is at the final stage. In fact, 5G standardization will wrap up with Release 17 early next year, and Release 18 onward will be called 5G Advanced. Of course, 6G standardization will kick off around 2025 after 5G Advanced standardization is completed. 5G Advanced should be developed so that it can meet new market needs while addressing the key issues identified during the initial deployment of 5G. A well-known major issue of 5G is shorter communication coverage compared with 4G. It is caused by the use of higher frequency bands and time division duplexing. 5G Advanced is expected to develop and introduce a new duplexing scheme to tackle this problem. It should also embrace new technologies such as AI/ML and support new terminal types such as XR devices while operating at diverse frequency bands. Now, let's move on to 6G, which is going to open up a whole new world of opportunities in the following decade. Overviewing the megatrends towards 6G will be useful for us to predict what 6G should look like. First of all, 500 billion machines are expected to connected by 2030, and it represents almost 60 times the world population then, meaning that machines along with human beings will be the main users of 6G. Given that the capability of machines can be far beyond that of human beings, 6G should be developed to meet the requirements of such highly capable machines. AI/ML technology is being utilized for performance enhancement and automation in various areas. And mobile communication is not an exception. AI/ML can be utilized for network planning, performance prediction and optimization of mobile communication, so that CapEx and OpEx can be reduced. This trend is expected to continue, especially given that mobile communication network is too much complicated to be monitored and configured manually. And the AI ML technology itself will continue to fast develop. While the network equipment has been heavily hardware-centric traditionally, more and more software-based solutions are being introduced thanks to the performance improvement of CPUs and GPUs. Along with that, use of open sources and open interfaces between network entities is becoming more popular too. This trend will allow us to build network in a more cost-effective and flexible manner. Finally, communications technology has been contributing to address social issues such as greenhouse gas reduction and education inequality, and it will continue with 6G. In fact, 6G should be developed to be a more eco-friendly green technology. Given these megatrends, we expect that 6G will enable such exciting new services as truly immersive extended reality, high-fidelity mobile hologram, and digital replica. While some of earlier forms of these services are available even today, they are not up to the customer satisfaction due to the lack of supporting technologies, including devices and communications technology. Today's 5G is not likely to be able to support full-fledged form of these services. To enable them, 6G should provide a lot better performance than 5G, including peak data rate of 1 terabps, which is 50 times that of 5G, and air link latency of 100 microseconds, which is 1/10 of that of 5G. We led in 5G advanced research back in 2009, and now we are at it again with 6G. We are currently looking at various candidate technologies to realize 6G. Those include terahertz bands, novel antenna technology, advanced duplex technology, comprehensive AI, and new network topology. I will talk about some of them in the following. 4G was defined to operate at up to 6 gigahertz, while 5G is being defined to operate at up to 110 gigahertz. To support the anticipated ultra-high data rate, we need to explore even higher frequency bands, say above 110 gigahertz. This high-frequency band, so-called terahertz or sub-terahertz, will allow us to utilize wide bandwidth needed for potential 6G services, as well as high-precision sensing capability. However, there are many inherent challenges, including severe path loss, poor RFIC performance, and so on. At the same time, 6G will also need to use lower frequency bands in a more efficient way as well. In fact, we have already demonstrated terahertz communications. As shown in the slide, the demo included a transmitter and a receiver composed of a 128-element antenna array and 140 gigahertz RFIC, which enable sharp beamforming. As shown in the video, the communication link achieves over 6 gigabps data rate. For the signal reception, the receiver uses a sharp beam formed by utilizing antenna array and RFIC. We observe that the data rate remains about the same even if we rotate the receiver, meaning that the receiver's beam is formed towards the transmitter adaptively, irrespective of the receiver's orientation. We believe that this demo made a notable progress in terahertz communication development, given that this kind of adaptive beamforming technology is crucially important to support high-frequency communication link in mobile environments. With 5G, massive antenna technology was introduced, and we expect even more massive antenna will be used for 60 terahertz to compensate the path loss, low PA power, and so on. We believe that metamaterial technology can be used in conjunction with massive antenna technology to enhance beamforming and signal propagation properties, potentially at a reduced cost. Meta-surface lens and reconfigurable intelligent surfaces are such good examples because they can adjust the beam direction of either penetrating or reflected signal to enhance the communication quality. Frequency division duplexing, or FDD, has been widely used for up to 4G, and time division duplexing, or TDD, is mainly used for 5G today. We are introducing a new duplex scheme called XDD, meaning cross-division duplex, as a means to extend the uplink communication coverage in TDD band as part of emerging 5G advanced standardization. 6G is expected to utilize all different types of duplexing schemes in an adaptive manner, depending on the environments. That will also include full duplex, which allows simultaneous transmission and reception over the same spectrum. In fact, we recently demonstrated full duplex technology over millimeter wave bands around 26 gigahertz. As shown in the slide, a base station and a mobile terminal were placed with 100-meter distance in an outdoor environment, where simultaneous transmission and reception occur with 100 megahertz bandwidth. This video shows the comparison between full duplex and TDD of 5G in terms of the total data rate. With full duplex, over 700 megabps total data rate is achieved, which is almost the double of the total data rate achieved with TDD. We believe that full duplex will be a key component of 6G advanced duplex scheme, which allows us to utilize the precious wireless spectrum more efficiently. As I mentioned earlier, AI/ML technology is being utilized for network planning, prediction, and performance optimization today. However, given that the technology up to 5G has been developed without AI/ML in mind, the performance improvement might be limited. We believe that 6G will be developed with AI/ML embedded natively so that it can be used to optimize the end-to-end performance from user device to application server in a comprehensive manner. Last but not least, we expect the network topology will continue to evolve to provide high-performance 6G connectivity anywhere, anytime, in a cost-effective manner. 6G should be available across the globe from the South Pole to the North Pole without service disruption. To meet the goal, 6G network should involve both traditional wireline and wireless backhauls, and even non-terrestrial networks such as satellites and urban air mobility. Last year, we released our 6G white paper, including our vision, various requirements such as performance, architectural, and trustworthiness requirements, and candidate technologies. Given that 6G is aiming for commercialization around 2030, its development will be a long, sweaty journey. We'll carry out our vision to bring the next hyper-connected experience to every corner of our lives in the following decade. Thank you very much for your interest and attention.